In the realm of wireless networks, caching and recommendation systems have emerged as crucial components to mitigate the surge in data traffic and enhance user satisfaction. This paper delves into the concept of recommendation-aided caching using Combinatorial Multi-armed Bandits, CMAB. The authors formulate the cache hit optimization problem as a CMAB problem, where the goal is to maximize the cache hit probability by jointly deciding what contents to cache and recommend to users. The system model consists of a wireless network with a base station connected to content servers via the core network. The base station has a cache that can store up to C contents, and there are U users who can request contents. The caching and recommending decisions are taken at the slot boundaries. The authors introduce a caching vector Y and a recommending vector X for each user, where Y and XUI denote whether the ith content is cached and recommended to user U, respectively. The request probability of user U for file I is modeled as a convex combination of the original preference distribution and the preference distribution induced by the recommendations. The authors assume that users select contents from the recommended list uniformly, and the request probability is boosted for recommended contents and decreased for non-recommended contents. The content caching problem is formulated as a CMAB problem, where the goal is to maximize the sum of the cache hit probabilities across all users, subject to cache capacity and recommendation constraints. However, the user preference distributions in the absence of recommendations are unknown, making it challenging to estimate the request distributions. To address this, the authors propose a UCB-based algorithm that estimates the request distributions and solves the optimization problem. The paper provides an upper bound on the regret of the proposed algorithm and numerically demonstrates its performance compared to existing algorithms. The authors highlight the significance of jointly considering caching and recommendation strategies to enhance caching performance. Future directions include exploring the case where the position of contents in the recommended list affects the request probability and estimating the probability of users accepting recommendations. Here is a combined summary of pages 3 and 4 of the research paper. The authors propose an UCB-based algorithm to solve the cache management problem with recommendations. The algorithm aims to maximize the cache hit rate by recommending cached contents to users. The authors define the regret for not caching the optimal contents and propose an algorithm to estimate the optimal set of cached contents. The algorithm works by estimating the preference probabilities pi's for each content I and constructing a UCB index UI, t, equals pi, t, plus d, t, for each content I, where d, t, is the confidence interval quantifying the uncertainty in pi, t, at time t. The algorithm chooses the top C contents with the largest index and recommends any R contents out of them. The authors provide a regret bound for the proposed algorithm, which is characterized by Theorem 1. The theorem states that the expected regret of algorithm 1 is bounded by a function of the confidence interval, the number of contents, and the mean of the recommendation-induced preference distributions. The authors also provide a remark on the assumption of uniform recommendation-induced preference distributions and discuss how the algorithm can be extended to more general distributions, such as ZIF distributions. Additionally, they discuss the importance of incorporating user preferences into the recommendation decisions and propose it as future work. The authors further provide a lemma that defines an equivalent regret definition and use it to prove Theorem 1. The proof involves bounding the expected cumulative regret associated with each content k element of n, y and decomposing the indicator function into two parts. Overall, the authors propose an UCB-based algorithm for cache management with recommendations and provide a regret bound for the algorithm. The algorithm is designed to maximize the cache hit rate by recommending cached contents to users and takes into account the uncertainty in the preference probabilities. The paper presents a UCB-based algorithm for content caching with recommendations, modeled as a Combinatorial Multi-armed Bandit, CMAB, problem. The authors provide an upper bound on the regret of the algorithm and numerically evaluate its performance compared to existing algorithms. The regret bound is derived using Hoeffding's inequalities, which bound the probabilities of events related to the estimated probabilities of content requests. The authors choose a specific value for the parameter "la" k to ensure that event 3, which corresponds to a high regret, cannot happen. This leads to lemmas 2 and 3, which provide upper bounds on the expected regret. The numerical results show that the proposed algorithm outperforms the standard CMAB UCB algorithm, the greedy algorithm, and the E-greedy algorithm in terms of regret. The performance of the algorithm is evaluated for various system parameters, including the weight of recommendations, WREC, U, the exploration parameter, alpha, and the distribution of recommended contents, uniform and ZIF. The results indicate that the regret decreases as WREC, U increases and becomes close to 1, and that the performance of the algorithm is robust to changes in alpha. Additionally, the authors find that having a ZIF distribution over the recommended contents yields the same performance as a uniform distribution. The paper concludes by discussing future work, including considering a different recommendation model, incorporating recommendation quality into the problem, and handling unknown WREC, U values. The references provided include related work on Kachingaware recommendations, joint optimization of caching and recommendations, and caching efficiency maximization. Here is the combined summary of pages 7 and 8 of the research paper. The appendix section provides proofs for lemmas 1, 3, and 2. The proof of lemma 1 involves rewriting the expression for R, T, using the definitions of x** operator UI and x, T, UI, ultimately simplifying it to txi element of eptxt equals 1I element of y, t, p. The proof of lemma 3 begins with a bound for the same la, k value, which is then rewritten using the definitions of increment E1, k, increment E2, k, increment EC, k. These values are used to redefine y as a for all I element of 1, 2, c. The right-hand side of the bound is then rewritten as a maximization problem, which is solved by setting nay, k, for all I element of 1, 2, 3, c, to maximize the expression. This leads to a bound for the expectation of the sum of increment e, k. The proof of lemma 3 also utilizes lemma 4, which provides a tighter bound for the sequence of positive numbers increment 1, increment 2, increment k. This lemma is used to bound the expectation of the sum of increment e, k, resulting in an expression involving m, increment min, k, and alpha, WREC. The proof of lemma 2 involves bounding the second term of equation, 18, which is done by splitting the expectation into two events and applying the probability bounds from equations, 19, and 20. The resulting bound is then simplified using the assumption that for 1 WREC, 1, eta greater than 1 and la, k greater than 1. Finally, the bound is used to write an expression for the expectation of the sum of increment e, k over y. Overall, these proofs provide key results for the paper, including bounds for the expectation of the sum of increment e, k and the second term of equation, 18. These results are crucial for establishing the main theorems of the paper.